Hello, pre-calculus students. Today we're going to talk about exponential and logarithmic functions. This is the start of our next unit, chapter 3 in your textbook. And I've got an image for you. This is actually a picture from a National Geographic magazine. This is 11.9 tons of spent nuclear reactor fuel. This is confined in steel cylinders behind glass walls at a government facility in Idaho. Basically, if you came in contact with any of this, you would instantly die. Now, I'm starting with this depressing image because nuclear waste has a half-life, meaning that after, I don't know what the half-life is, but after perhaps 1,000 years, only half of the life remain, or half of the waste remains. After another thousand, half of that remains. After another thousand, half of that remains. Basically, half-life means that this nuclear waste is never totally gone. There's always half remaining after a certain amount of time. Now, a lot of things in life follow this same kind of pattern. For example, if you ingest drugs into your body, after a certain amount of time, half of the drugs are gone, are like swept out of your body. After that same amount of time, half of what remains is still there, etc., etc. Which is why if someone were to take drugs or drink alcohol, there is some effect immediately, but then after a while that effect wears off. And trace amounts of whatever that is still remain in your body after any amount of time. That stuff will stay with you forever. Maybe can't be measured, but it is still there. So that is a little bit about what half-lives are about. These are exponential functions, which is what we will be studying for the next couple weeks. So let's just talk about these exponential functions. So exponential functions have this form right here. And I'm just going to write just a more, not a more, a more specific form of this. Y equals 2 to the x. And if you were to graph y equals 2 to the x, this is like saying x is your power, so you could say x to the 0, x to the first, x to the second. And if you can envision this, as the power goes up, the graph goes up quite a bit, and it follows a curve kind of like this. And in general, population of a country, a city, follows the same kind of format because your population tomorrow is based on your population today. So if your population grows steadily, there will come a point where it will increase like so. If you have investments, investments follow the same pattern. Money in a savings account does not grow much at all, but at some point that investment will start to pay off and it will really start to grow, depending on your interest rate and time and some other things in there as well. If you buy a car, for example, it follows an exponential function, but instead of increasing in value, it decreases. So it might look something like this. It decreases in value very quickly, but then it levels off because it can't really go down forever. I'm going to get rid of that, but that is an exponential curve. So the value of a car, of an investment, the population of a country follows an exponential curve. Now, logarithmic curve, we can rewrite this logarithmic curve by saying, hey, let's start with this base and say a to that power, a to the y power, is equal to x. Now, same kind of function, so we could say 2 to the y equals x. Same kind of function, but we're switching x and y. As we know, when we switch x and y around, we get an inverse function. So this curve would look something like so. And it's what's called a logarithmic function. Now, logarithms were developed to solve a specific kind of problem, which we are going to see here in this unit. So, although logarithms, many students do not like them, they are very useful to us, and they're developed because without logarithms, there's a specific kind of problem that there is no other way to solve, and we'll talk about those throughout this unit. Okay, so let's jump right in. Our first example says convert the following logarithmic equations to exponential equations and convert the exponential equations to logarithmic equations. So we should be able to go back and forth between exponential and logarithmic. And once you know how to do this, it's relatively simple to do. This one task is the most useful thing you can know how to do when dealing with exponential and logarithmic functions. So let's talk about this. So this says y equals log base 2 of 16. Now really a logarithmic function is the inverse of an exponential function. So any logarithmic function you can write as an exponential function by starting with the base. So we start with the base and we say 2 to some power. What's the power? Well, the power is this answer. So I like to start here and say 2 to some power, which is your answer, is equal to this number here, 16. So we can write any logarithmic equation as an exponential equation by following those steps. Likewise here, start with your base. X to some power, here's your power, so x to the fifth equals this answer 32. Same thing here, 4 to some power, and here's your power, 4 to the third, equals this answer here, x. Now, in many cases, it is much easier to solve these equations once they're written as exponential equations rather than logarithmic equations. Now, on the other hand, sometimes it's easier to go the other way around. So if we start with an exponential equation like these, it's easier to write it logarithmically. Well, remember, this number that's out here in front, this is your base. This power is your answer of your logarithmic equation, and this number out here corresponds with this number in the logarithmic equation. So, for example, we could say, okay, this 6 is going to be your base, 3 is your answer, so we can say 3 equals log base 6 of x. So 6 to the third power equals x. Likewise, over here, we could say 4, the power equals log base x of 625. And one more of these, we could say x equals log base 3 of 81. So being able to go back and forth between exponential and logarithmic functions, that is a hugely important skill in this next unit. If you can do that, that will make your life much, much easier in the upcoming couple of weeks. Okay, so that's one skill we'll need to know. Let's talk about something else. Let's graph some of these. So first equation, y equals 3 to the x power. Actually, graphing this isn't so bad. We can make a table of values, x and y. And let's plug some different values in place of x. So I'm going to say -2, -1, 0, 1, and 2. So if we put -2 in here, we have 3 to the negative second power. Now recall, something to a negative power is the same as 1 over that number to the positive power. So the negative power does not make this value negative. It's a way of saying, hey, we're going to take the reciprocal of that value. So 3 to the negative second is 1 over 3 to the second, which is 1/9. 3 to the negative first would be 1 over 3 to the first, which would be 1/3. 3 to the 0, anything to the 0 power is 1. 3 to the first is 3, 3 to the second is 9. So let me plot those points. So -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9. Now these exponential curves always follow this same basic format. In this case, the x-axis is an asymptote, meaning this curve will approach that axis but never touch it. This graph does go up on and on forever. It will go over, so we could put a number like 10 in here and we get something infinitely high up above. But there is your graph of y equals 3 to the x. Now, graphing this next one appears to be much, much more difficult. But let's rewrite it as an exponential function. So we could say 3 to the y power equals x. Now we could plot some points here. I could make an xy table. Choosing x is very difficult, but we can choose y. And you'll see that if we choose these same values for y that we previously chose for x, we'll get new x values which are similar to our original y values. And that makes sense if you think about these functions here, that these really, on the two functions, we're really just switching x and y. So these are inverse functions. So plotting these new points will give us a curve that looks something like this. And in fact, if I think about the graphs of inverse functions, it makes sense that we're seeing the same points with the x and y values switched around. On the graphs, we're seeing this mirror image across the line y equals x. Exponential functions and logarithmic functions are inverse functions. Now, next year when you take calculus, you'll deal a lot with this number e. Now, e, I'm sure you saw in your Algebra 2 days, and you might not have ever really realized what e was all about. Well, first of all, what is e about equal to? Well, e is what's called a transcendental number, kind of like pi, meaning it's one of these decimals that goes on forever and never repeats. Now, I guarantee you, this is a test question. I'm going to ask you on your next test, what is the value of e to 15 decimal places? Well, guess what? Your calculator does not keep 15 decimal places. So this is something you're going to need to know. Here's what it is. It is 2.71828 182845945, and it goes on and on forever without repeating. Now, how on earth are you going to know that for your next test? Well, look at the pattern here. It's really not so bad. We've got 2.7. You should be able to just remember that much. 1828, 1828. Okay, we can remember that. 1828, 1828. Then take a look. 45, 90, 45. Those are the angles of a special right triangle from your geometry days. So you will need to have that memorized. I guarantee you it's a question on your next test. Now, what does it mean? What is E? Well, by definition, here's what E is. E is the limit as n approaches infinity of 1 plus 1 over n to the nth power. Meaning, we put bigger and bigger values in place of n. So if you put 2 in place of n, you get 1 plus 1 half to the second power. Put 3 in place of n, put 100 in place of n, put 1,000 in place of n. You'll notice what's in here will be 1 and something left to some huge power. Now that's what E is going to be equal to. Try that on your calculator. Put a number like 1,000 in place of n, and you'll get something very close to what we have up here. The bigger n is, the closer it will be to this decimal. That's the definition of E. Now why is it important? Well, it's important because if we graph the function y equals e to the x, it'll be one of these exponential curves. But it is a special unique exponential curve. What's special unique about it is if you found the slope of the line that just touched that curve at one point, the slope of that line is always going to equal the y coordinate right here. So no matter where you find a y coordinate, the slope of the line that just touches at that point is always equal to whatever that y coordinate is. All right, that's a unique function, guaranteed. You'll see that again in your calculus class. But we're going to deal with it a little bit in pre-calculus as well. Okay, so let's go on to our second and final example in our notes. Actually, not an example, but a couple formulas we're going to see. Now, these formulas are very important to you guys because these formulas have to do with making money. And everyone likes to make money, so let's talk about these formulas here. This first formula, the one on top, the amount of money, so this A stands for final amount. So I'm going to label that. So the amount of money you make. So we're going to talk a lot about how can we possibly make $1 million, let's say. We'd put 1,000,000 in place of A. And actually this second formula, same thing. So A stands for the amount you want in the end. Or it could be the amount that your car is worth, or the amount that your house is worth. Or even thinking of people, the amount of people who live in the US or who live in China. Your final amount. P is your principal. Principal is the amount you start with. So if you're starting with $1,000, how can you invest that so you end with $1 million? P is your principal, the amount you start with. R is the interest rate. So if you are earning 5%, do not put 5 in place of R, put 0.5 in place of R. It is a percent. So R is your interest rate. T is your time. In these formulas, T is in years. There are some formulas where T might be in months, but T is in years. And N is the number of times that interest is compounded per year. So if your bank gives you interest monthly, or daily, or yearly, how many times you get that interest per year? That's N. So it's best to get that interest more often. Now, if perchance you get that interest continuously, not just every second, but constantly, then we use the second formula. So I'm going to put compounded continuously. And no banks are ever going to give you interest compounded continuously. However, if we use this formula for something besides money, like let's say the population growth in China or population growth of bacteria in a biology lab, this second formula makes a whole lot more sense. Okay, that wraps up what we need to go through to start this unit. There is an assignment, kind of a lengthy assignment, but some of these problems go rather quickly. So once you've completed this assignment, you may move on to the next set of notes.